And?
Imagine if we could look so closely, we could see each grain, each particle. You see, there are patterns in everything.
Integrals, infinite series.
I've never seen anything like them. From an Indian...
From Hunter College. My name is Isaac Berry, and welcome to lecture number 18. Today, we're doing continuity and limits. So, last time, you might recall that we went over this very interesting function. So, it's a function that's 1 if you're a rational number, and it's 0 if you're an irrational number. And, of course, it passes the vertical line test, because something can't be both rational and irrational at the same time, which means this is indeed a valid function. So this is a function where it's 1 if x is in the rationals, not the reals, the rationals, and 0 if x is in the irrationals. So this is continuous absolutely nowhere. So, you want to see something else really cool? Let's say we have something that's continuous at exactly 1 point. What would you imagine that would look like? Well, it's pretty easy. All you have to do is, if x is in the irrationals, make the function equivalent to 1, and if f is in the rationals, make the function equivalent to x. And so, our function is continuous at exactly 1 point. X is equivalent to 1. You can probably see the pattern here. If we want it to be continuous at 2 points, we can use a parabolic shape. If we want it to be continuous at infinite points, we can use something more diabolical, like a sine wave. Now, what if we wanted something very diabolical? What if we wanted it to be both infinitely continuous and discontinuous at infinitely many points in a bounded interval? You see, you have to go from 0 to infinity, or 0 to minus infinity, or minus infinity to infinity, or somewhere in between that, in order for there to be infinite points at which this is continuous. However, what if you could have that all condensed into a bounded region? Well, that's what this function is for. It's 1 if x is equivalent to 0. It's 1 divided by n if x can be written as m over n in lowest terms. To make sure it's actually a function, we have to make it lowest terms. And it's 0 if x is irrational. So then, what does it look like? Well, you've got a sprinkling of zeros. Got exactly 1 at x equals 0. And then 1 over n. Well, let's think about it. Let's say we were at 1/2. Then what would it look like? 1/2. Dot. Then let's say we were at 1/4 and 3/4. Well, they'd give us the same exact value, 1/4. If we go 1/8, 3/8, 5/8, 7/8, they'll all give us 1/8. 1, 2, 3, 4, and so on and so forth, kind of looking like a tree diagram. And this thing will just continue going on. And as it turns out, this is fully both continuous at any rational and discontinuous at any irrational, which, since both of them are dense in R, that means that it's both infinitely continuous and discontinuous in any bounded interval. Now I have a very big question for you. Can we swap these around? What do you think? Leave your answer in the comments below. So, let's just swap it back to the correct order for this one. Now, let's move on to a very interesting topic. Let's see what a limit is. But wait, Saborno, you covered this like 8 lectures ago. Yeah, that was the limit of a sequence. We have A1, A2, A3, A4, A5, till we've got some point of no return, AN, and then everything is in the epsilon neighborhood of the limit, L. Alright, but then, what does the limit of a function look like? Well, it's very similar. Instead of just one Greek letter, all you have to do is use 2 Greek letters, the Epsilon-Delta definition. Here we've got a similar zone of no return. If we can take some point C and then we trace that out, and it goes over to f of C. I'm an expert in drawing dotted lines, as you can see. F of C, right over here. Now, let this be C minus epsilon, and this be C, delta, and this be C plus delta. Alright, so now, all we're going to have to do is take this, which goes right over here, and this, which goes right over here. Now, the maximum over here is f of C minus delta, and the minimum is actually neither of these three. It's this point right over here. So, then we can put a little zone around f of C. And what is this zone supposed to be about? Well, we want every point from here to map to a point in there. So if something maps to a point outside, then that's a no-go. So we want to essentially find some minimum epsilon value. So, for example, we know that this minimum over here traces to this point, and this maximum over here traces to this point. So that means that the minimum epsilon neighborhood would just be from here over to here. F of C plus delta F of C minus F, how would I write this? F of C plus delta minus F of C and F of C minus that all. Or if we were to write it more elegantly, 2F of C minus F of C plus delta. So that's just one example. Now, the simplest way of going about things is when you just have a constant slope, like this line over here. Let's call it 2y equals 2x, for example. So now, let's say I pick some point, C. So then, f of C, which is going to be right over here on the y-axis, that's just going to be 2c. So then what happens if I take c minus epsilon and, delta, and c plus delta? What's the minimum epsilon neighborhood I have to use so that every single point in between this area will map over to here? Well, let's try it out. C minus delta goes right over here and becomes 2c minus 2 delta. And over here, we've got 2c plus 2 delta. And here's the thing. The derivative of this thing, which, yes, I know we can't define without the limit, but informally, we can see that if we make a sequence out of all of these points, it's always increasing. If A is greater than B, that means f of A is greater than f of B. So, in a similar fashion, we can say that, well, obviously it's simple logic, 2A is greater than 2B. So, in a similar fashion, we can say that if C is between A and B, f of C is always going to be in between f of A and f of B, no matter what C is, as long as it satisfies this inequality. So I think we should actually use a different letter. Why don't we call it N? So then, let A be C minus delta, and then Fn, Fc plus delta. Because, of course, 2c minus 2 delta is going to always be less than 2n. This is always going to be less than 2c plus 2 delta. So you see, anything that's in between these 2 points on the x-axis, their output will lie somewhere between these two on the y-axis. So we don't need to worry about maximums and minimums by the intermediate value theorem. Okay, I can't say that when we haven't even proven limits yet. So, by our knowledge, that means that this is the minimum epsilon neighborhood. But wait, we still haven't determined the value for epsilon yet. What is this? Well, we know that 2c plus epsilon has to be greater than or equal to 2c plus 2 delta. 2c minus epsilon has to be greater than or equal to 2c minus 2 delta. So, it seems pretty obvious, epsilon has to be greater than or equal to 2 delta. Sorry. We formalize the proof of what epsilon is supposed to be with functions. Well, all we have to do is say, we know x minus c is less than delta. Now, we want to take f of x minus L is less than epsilon, and we want to find epsilon in this manner. So let's try this example. We have that x minus, we can pick any value of c we want, but for this example, I'm going to pick a special number, or a funky number like 7, is less than delta, and you get f of x, which is just 2x, minus, what's the limit of 2x at 7? It's 14, but that's what we want to show, is less than epsilon. So then, given a delta, we want to find an epsilon that works. So what delta we want to choose? Well, it doesn't have to be something too big. Let's say 0.5. So then, what does epsilon have to be? Off the top of your head, you can guess that it's going to be 1, but we actually have to check. This is exactly the same thing as this, right? So then, we know that x minus 7 is less than 0.5. So 2 times x minus 7 is less than 1, which means that 2 times x minus 7 is equivalent to the absolute value of 2x minus 14, which is less than 0.5 and less than epsilon, which means epsilon has to be greater than or equal to 0.5. There we go. So now, let's try it with an example where the slope is changing. Let's say you've got x squared. All right. So we've got x squared right over here. But the slope is changing every which way. So what do? Well, all we have to do is choose a specific point. So let's say the specific point is 5. Yeah, 5 sounds like a cool number to do it with. Draw this dotted line, and of course it leads up to 25. I know, very accurate drawing. 25 is definitely smaller than 5. Blah, blah, blah. It's 2 scaled. So, we then get what? We know that x minus 5 is less than delta, which we can pick to be something small. Let's say 0.5. Then we have that f of x, x squared, minus 25 has to be less than epsilon. So what's the minimum value of epsilon over here? So all we have to do is something very similar. This is just x minus 5 times x plus 5. But wait, things get slightly more complicated from here. We can't just say x plus 5 is less than epsilon over x minus 5, and then abracadabra your way to the answer. We need to have an explicit form for epsilon. We need to have that explicit upper bound in terms of x and some number to actually solve equations like these where our slope is constantly changing from one point to the next time.